When we talk about radiation protection, we will discuss some parts that we mentioned at the beginning briefly, and then we will talk about radiation protection in good detail. Initially, when we talk about radiation protection, we will discuss a specific step. Well, if I were to ask you now if there is radiation around, there is definitely radiation around. In the situations I am in, there is certainly radiation present, whether from mobile, phones, laptops, or if there is a microwave nearby, or radio waves, or if there is a TV nearby. All of this emits radiation. Even ceramics, the flooring and the walls all have a certain level of radiation. Even when you walk in the street, you will find that you are exposed to some level of radiation. Exposure to radiation is present around us, but not all forms of radiation are considered harmful. Not all types of radiation that we are exposed to are harmful to us. I cannot smell radiation or detect it with my senses. I cannot hear radiation or touch it unless it is within the visible range of radiation. This is the situation where you can see the colors contained in visible light, which has a certain wavelength range within the electromagnetic spectrum. The idea is that you can sit in front of your laptop for a long time, and in front of your mobile phone a lot, and in front of the TV a lot, but you cannot enter the area of X-ray or fluoroscopy, or the area that contains a source of radiation, even if it is an open source of radiation. We are talking about radioactive material, for example. You cannot enter into radioactive materials, for instance, in certain radioactive materials and be able to return to them for a period. The idea is that I have these types dependent on the energy of radiation. When I talk about the ordinary types I deal with, like mobile phones, laptops, microwaves, and things that are considered low energy, I call them non-ionizing radiation. But the types that are considered to cause effects, I call them ionizing radiation, such as X-ray or gamma ray radiation. But the types that are considered to cause or have an effect, I call them like. So where is the lesson or the problem? The whole problem lies in the energy of the radiation. Is the energy sufficient to knock out the electron from the atom, or is it insufficient to do so? If my energy is sufficient to knock out the electron, then ionization has occurred, and I have entered the realm of ionizing radiation. In this case, you are at risk of experiencing an effect from the radiation. However, if the energy of the radiation is insufficient to cause this ionization to knock out the electron from the atom, then I would call it something like, for example, and greater than an example in the text ends abruptly. Is MRI considered ionizing? It is not considered ionizing, it is non-ionizing. A patient can enter the MRI room even in some cases, or according to certain regulations that state that a pregnant person can undergo the procedure without any problem, because it depends on energy loss through something called heat transfer. As we will discuss later regarding MRI safety or MRI physics, you can enter the magnet room where there is radiation, specifically non-ionizing radiation, but its effect is not to cause ionization in your body. It has other effects and safety principles. However, X-ray and gamma ray are the ones that cause ionization, and can knock out electrons from your body. In nature, we consume foods. For example, we all drink milk, eat rice, meat, fish, and spinach. All these common foods contain radioactive materials such as potassium-40, carbon-14, rubidium-87, tritium, and lead-210. Where does it come from? From the earth. And the nature of the earth itself during the agricultural process. There are things that come from cosmic radiation. There are things that come from the decay of uranium elements. These things come from agriculture. For example, if you want to plant something, there are certain materials that will be present in that area, such as potassium, carbon, rubidium, and thorium. These are considered common materials that have entered into this matter, and they eventually reach you through food and drink. However, these amounts are not large or concentrated enough that if you bring a radiation detector and measure from a certain distance or on someone's body, you would detect radiation. What you would detect is called background radiation. So if I take a survey meter or a radiation measuring device, it should not show 0 when I place it anywhere. There should not be an increase. You will find a certain value, which is called background radiation, and it can come from the earth or from the people present themselves. Why? I told you that one of the most famous radioactive elements present is potassium-40, which exists at a concentration of 0.01%. This abundance is significant. Regular potassium means anything that contains regular potassium has a potassium level of 40 radioactive activity at a rate of 0.01%. All right, so for example, if we talk about rice, you will find that the potassium concentration of 40 is present at 62.4 becquerels per kilogram. Becquerel is considered a unit of radioactive activity. What does a unit of radioactive activity mean? It means I come and say, I have atoms, and these atoms have feelings, as we mentioned before. If you remember, for atoms or nuclei to have feelings, there must be an imbalance in the number of protons compared to the number of neutrons, meaning there is an unbalance between the number of protons and neutrons. This imbalance leads to the nucleus itself becoming unstable. To stabilize, it either converts a proton into a neutron in the case of excess protons, or a neutron into a proton in the case of excess neutrons. The increase in the number of neutrons results in what I call decay, meaning the transformation of a nucleus from an unstable state to a stable state. If I say that this radioactive material undergoes 1 decay per second, then its radiation energy is measured in becquerel. What does that mean? It means that when I say the radiation energy of this radioactive material is 1 becquerel, it indicates that there is 1 decay per second, meaning every second an unstable atom transforms into a stable atom. Do you see decay per second? Is it just 1? No, that's a lot. So since it's a lot, I have to choose another one. They told you that 3.7 times 10 to the power of 10 decay per second is called 1 Curie. Or in other words, you can call it Curie. Just call it Curie. The term Curie means that this material undergoes 3.7 times 10 to the power of 10 atoms transforming every second. So, this is what the word Curie signifies. You will often hear the term Curie used, for example, when someone says, I have how many millicuries today? In nuclear medicine, they might say, I have 10 millicuries, or 20 millicuries, or 30 millicuries. This means that the radioactivity or activity refers to how many decays occur per second. The higher the activity, the greater the number of decays or the number of atoms undergoing decay per second. Big means no. The energy or photons that will be emitted as a result of this decay per second will be numerous, so the radioactivity is high. If I measure the dose rate with the radiation measurement device at a certain distance, it will give me a very high dose rate. Now, what brings me to this topic is the term becquerel per kilogram. Becquerel per kilogram refers to the activity present in a mass, which I call the concentration activity. The concentration activity means the concentration of the radioactive material by weight. For example, if I have 1 kilogram of rice and you take, for instance, 150 grams of rice that contains 62.4 becquerel per kilogram. For example, 142 flets remains 397 in the tables 135.2, and you find that the highest concentration, or one of the highest concentrations, is potassium 40. This means that potassium 40 is present in our bodies, along with other elements in different proportions, but the most abundant is potassium 40. Because potassium 40 emits beta particles, we said that as a result of this decay that occurs, it can produce alpha particles, beta particles, or gamma rays. We said that alpha particles have the shortest range because they are heavy and lose all their energy over a short distance. Beta particles, on the other hand, can travel a bit further, but the same idea applies. They can be stopped by materials like aluminum or plexiglass, while alpha particles can be stopped by a sheet of paper. This means that if I have beta particles inside my body, when they exit my body, I don't feel anything. If someone measures with a survey meter, they won't feel anything, but they are indeed present. Here I will give you an example of background radiation. For instance, as I mentioned, the nature of the land in Iran has high background radiation. Why? Because the land has mountains, and these mountains always contain uranium, thorium, and radioactive materials. These radioactive materials increase the background radiation. The more mountainous the land, the higher the background radiation level. For example, in a country like Iran, if you take a survey meter in the street, you might find 1.1 microsievert, while in Egypt, you would find 0.00 or 0.01. The difference in numbers is significant because this is considered normal, but the nature of the land itself contributes to it. For instance, in India, whether in New Delhi, Bangalore, Mumbai, or Kerala, or even in Brazil, and here in the UAE, this is dependent. In the UAE, for example, the microsievert level of background radiation is maintained. This means that radiation is present around us everywhere and we deal with it, but these radiation levels are very low. For example, when you compare the microsieverts, which is the radiation unit we have been discussing since yesterday, to the dose limit, for the public, you find it is 1 millisievert per year. Multiply this value by how much to reach 1 millisievert, which is 1,000, for example, so it is considered per year. For instance, you might find that a worker is exposed to 20 millisieverts per year, which is a very high value. Even if, for example, you take a flight and reach an altitude of about 15,000 meters above sea level, you will find yourself exposed to cosmic rays, experiencing about 10 microsieverts per hour. So if the flight lasts 3 to 4 hours, you could accumulate around 40 or 50 microsieverts during your flight at that altitude due to cosmic rays. Of course, if something like thunder or lightning occurs nearby, that radiation is not accounted for, but you can be sure that your radiation dose is very high. However, when I read a bit about this topic, it mentioned that the presence of thunder and lightning increases the cosmic radiation levels. If there is exposure during the flight, this increases the absorbed dose or the dose received by the passengers on the flight. All right, okay, I understand completely and fully. Radon gas is also one of the things that is considered to have a significantly high level, accounting for more than 50% of certain sources, even in the USA, such as in the environment. It results from the natural decay process of radioactive materials found in the ground over time. Being a gas, it can gradually accumulate, for example, on the walls of homes and even in the kitchen in various areas. The gas that is released can carry radon gas from the ceramic materials present in houses. The problem with radon is that it can cause serious inhalation issues and potential risks, which may lead to health problems. Radiation exposure. Therefore, it is advised to always have good ventilation in homes to allow the gas to escape, or to have good ventilation in the kitchen to prevent this gas from accumulating or reaching high levels on the ground or on the floors in the house. The question here is, do I really need to do this today? If I came to say that I need radiation protection and to address the radiation incidents that are happening, okay, never mind. In fact, when you actually drink some coffee, the amount of energy it provides to your body is about 67 calories. This energy, in reality, is equivalent to the amount of energy you would absorb if you were subjected to a lethal dose of radiation, which is 4 grays. So, the lethal dose of radiation equals the amount of coffee you just drank, right? However, the key point is in the effect. The effect of radiation, or its interaction with our bodies, is obviously different from that of coffee. We are talking about the energy that enters your body, but this is the problem and the disaster that arises from radiation incidents like nuclear bombs, such as Hiroshima and Nagasaki, or an explosion like the Chernobyl reactor. This leads to something called epidemiological studies, which deal with the people affected by radiation effects. Essentially, these studies are crucial for understanding the long-term impacts on human health. To put it simply, while coffee and radiation might deliver similar energy levels, their effects on the human body are vastly different, and this distinction is critical. In some cases, or in certain situations, accidents that take place, like the ones we have here, for instance, this happened as a result of CT brain perfusion, where a dose of radiation reached a level of approximately 3 to 4 gray, resulting in a deterministic effect and causing damage. As we know, we use a lot of scans in the area of the circle of wheels to see how the traffic flows in this area. Are people moving back and forth in this area to see what is happening there? For example, if the parameters are elevated or if the scan time is extended, it can start to give you a very high dose. This elevated dose can potentially cause significant deterministic effects. For example, people working in interventional radiology may notably experience this to the extent that one of the largest organizations, the International Commission on Radiation Protection, provides recommendations for radiation protection. If you find that skin burns occur in this way, or that erythema happens after coronary procedures, which may occur weeks or months later, it indicates that there is an effect from radiation even at the level of patients, and their exposures in the usual procedures we perform every day, such as cardiac, angiography, including other related procedures. Even the interventional radiologists who work with a lot of it can be affected due to improper use of the machines, which leads to radiation exposure. You might find someone using the continuous mode with high doses or high parameters without taking any delays. For example, they might use pulse mode but with a high frame rate instead of a low frame rate. All of this increases the radiation exposure, and if some of them are affected in their eyes, these are all indications that there is a radiation effect. Many studies discuss this, even at the level of CT imaging. For example, you might find that during a CT scan, if someone is undergoing an angiography, they may receive arterial board imaging and portal venous imaging. They may also receive additional markers. If you come in simple terms, you will find the kV high, and you will find the milliampere high, and you will find a dose that, if you calculate it later, as we will see, can reach 90 millisieverts. This is a very high dose. I mean, 90 millisieverts. We are talking about a dose limit for workers of 20 millisieverts. Okay, the effect of this radiation is a certain threefold, but when we talk later about stochastic effects or random effects of radiation, as we will discuss, this probability increases with the increase in dose. Of course, we need to do something because it can cause, or even whether it is, okay, this can cause skin burns, whether temporary or permanent infertility, or even genetic effects. Okay, this is the discussion. So we know that we need to protect against radiation, and we will talk about the mechanisms of radiation protection. But before we delve into the mechanisms, you should know that there are three categories involved in protecting against radiation: the medical category, the occupational category, and the public category. The medical category includes patients. For example, if I have someone in research or a patient involved in research or something, or in like AEEE, like training, or also refers to people who are exposed to the devices themselves, whether the purpose is diagnostic or otherwise. They are considered under the medical category. You are talking about the staff, the workers, the radiation workers, such as the radiographer and the radiologist, the people who work in the field itself and who operate your machine. The public spawner refers to ordinary people, like, for example, if I have a place in a radiology center, someone in the waiting room is considered public. If there's someone working in the office next to me, they are also considered public. The person in the apartment above and the one below are all public. The idea of public exposure or protecting them primarily relies on shielding, meaning proper shielding calculations for the machine to mitigate the effects of radiation or reduce the dose that will reach the person present to the permissible dose. So I perform certain calculations and specific assessments to determine the thickness of the lead, concrete, or wall that will reduce the intensity or dose rate for the public. All of this is about shielding. And at the same time, for example, the distance means I have a free principle. Shielding is a very strong factor. There is also an inverse relationship between distance squared. The further away you are, the more protection you have. Therefore, if I have someone far away from me, I can protect them better. If someone from the community is close to the radiation source for a short time, then the time factor reduces the radiation protection or the radiation hazard they might be exposed to. Time, distance, and shielding are the three main concepts of radiation protection. These are the basics, but the techniques can vary. For example, you might say that the shielding from debris is shielding, while someone else might say, no, I will wear a lead apron under your umbrella of shielding. Another person, for instance, in interventional radiology, uses a ceiling screen, which is the lead glass. This type of shielding is also lead glasses, which are the glasses that contain lead to protect the eyes from radiation effects. This is shielding. Gloves, which are lead gloves, are also a type of shielding to protect the hands during exposure or when dealing with radiation. All these are forms of protecting the people who work for you. If someone comes from a place with radiation, are you going to leave them in the air? No, you have to implement specific measures with special calculations to prevent exposure. So you have these basic principles. Now, regarding the exposure time for the worker and the patient, even in the parameters you are working on, for example, you might say, I will increase the exposure time for the patient. You will work with a specific mode. This mode might reduce the exposure for the patient or reduce the frequency of the pulses or frames coming in. So, increasing the number of frames or decreasing the number of frames means you are either increasing or decreasing the exposure time. Now, for the person working with radioactive materials in the hot lab, do they spend more time or less time? This is also a time factor. Okay, the scan adjusts the machine's protocol by reducing or increasing the time of the scan. That's the time factor. Thus, the radiation sector also considers the time factor for the staff present because, consequently, if the time factor decreases, the radiation exposure time will also decrease. In this case, the exposure for the staff will also be reduced. Look, I take the three things and apply shielding. Time, distance. The distance I maintain from the source, okay? The X-ray tube, how far it is from the patient, that's the distance. So, I am working on medical exposure as well. And while I'm talking as a worker, where should I stand, for example, in the C-arm? Should I stand on the tube side or further away? If I'm working in my operating room and I have a C-arm, where should people stand? Close or far? That's the distance factor. These are things that must be in our minds while we are working. Time, distance, and shielding are very important to protect the patient, the public, and the workers who are present. The techniques differ based on the situation, but in the end, the principles are the same, the ideas are the same, and our basics are the same. So, you have three things, which are the three fundamental principles. What is this topic about? What is this topic about? I have, as I said, I have this and I have that. Honestly, right now, after the case, for example, the team conducts the examination